There you have it. Your first crude amplifier. With only one resistor, one capacitor, two transistors, and you have some sound popping out of your speaker like nobody's business. With a 12-volt power supply. This transistor is becoming hot. It needs to be heat sinked. Let me shut it down. Okay. Hello there. Welcome back to the Practical Electronics channel and to our third lesson. Today, we shall look at the bipolar junction transistor. We will particularly examine its beta characteristics with the help of an LED and an incandescent bulb. Then we'll build our first crude amplifier, even though it will work to our greatest fascination. And then we'll see if we can operate the transistor as a switch. We'll revise our assignment in lesson 2, and then we'll take our assignment for the day. Let's get into it. So today we shall use our breadboard again. Our straw head LED is here. We shall use it to demonstrate the beta feature of the transistor. Some incandescent bulb is here. We shall use that one too. I have this transistor which we shall rely on. It is 2N5551. If you don't have this and you get 2N2221, it will just suit your purposes fine. You just have to get a data sheet for the transistor. Data sheets are public documents covering semiconductors that are used to build electronic devices on the internet. They are public documents. Just look it up in Google and you have hopefully a PDF format to download and use as a reference material. We also use this transistor, TIP41C. Get a data sheet for it too. It will tell you the maximum voltage you apply to either the collector, the emitter, the base. It will tell you which voltage, when applied to you, will break down the transistor. It will tell you the maximum collector current. It will tell you its beta, which we shall be getting into pretty soon. We shall use this capacitor, and this 100 microfarad, 10 volts. We shall deploy it. I also have this relay to which I have attached some cables. We shall use that one. When it gets to operating the transistor as a switch, we shall use that one. Again, we shall also use some resistors. I have some resistors in my hand. I will tell you the values when the time is right. We shall use these ones also. And then, because we'll be building an amplifier, I have with me our output device, a speaker, with cables attached to the back. This is what to reproduce the sound from the amplifier. And then we have our stereo jack, which we shall attach to our laptop to give us the sound which we shall inject onto our breadboard. Let's get started. In my attempt to explain bipolar junction transistors, I'll be using the electron flow principle, which actually says that electrons flow from the negative terminal to the positive terminal. Some people rely on conventional flow, but I believe that if I use electron flow to offer the explanations, you understand it better. So we'll be using electron flow. Now, transistors come in two flavors. We have NPN and then PNP. The directions of the arrows on the emitter determines whether it is an NPN. So whether the arrow points to the ground, it is an NPN. Where it points away from the ground, it is a PNP transistor. Fine. Now, how does a transistor work? In fact, to engage the transistor to work for you, you put a positive terminal to the collector plus VCC, and then a negative terminal to the emitter. And then a positive terminal is applied to the base. This is how it goes. Now, to make this clear for you, let me separate this thing so you know what I'm talking about. Now, look at the way I have redrawn the transistor. You notice that there's now a separation between the collector terminal here and the emitter terminal here, which means current cannot flow directly from the emitter to the collector. It will have to go through the base. So both the emitter and the collector are attached to the base. But the base presents a barrier here, which prevents current from flowing from the emitter to the collector. I don't want to use terminologies like depletion layer, holes, electrons. No, those terms will leave us all confused. I want our presentation to be as simplistic as possible. So, in order for current to flow from the emitter here, which will go through the base into the collector, we must break this barrier which is inhibiting the current from flowing from the emitter to the collector. And we break that barrier by injecting either some voltage, minimum 0.6, because this is a silicon-based semiconductor, 0.6 or 0.7, or some small base current. And then we get a larger current here. So say we apply a current of 1 milliamperes. We could get 100 milliamperes at the base. That would depend on a particular variable of the transistor called the beta. It is usually labeled this way on the transistor, HFE, which is the beta. The beta is not a fixed variable. It is usually quoted on the transistor for you as a range. So some transistors, usually small signal transistors, will have it very wide, maybe from 100 up to 500. Others could have it from 50 up to 250. So it depends on the transistor. So our intent here is to inject a small current at the base, hoping to break a barrier here so that a large current will flow from the emitter to the collector. So this is how the collector current develops. This base current, like I mentioned earlier, is multiplied by its beta. So over here, if the transistor decides to use a beta of 100, what it means is that if you multiply 1 milliampere by the beta, which in this case is 100, you get a collector current of 100 milliamperes at the collector. Very simplistic, right? Yes, it is a very simplistic view of the transistor. But for somebody who is just getting introduced to the bipolar junction transistor, I believe it is just good enough. So let's build a circuit to illustrate what we are talking about. Okay, so I want to inject this transistor onto the breadboard. If you are not sure, the pin in the middle, that's the base. The one here is your collector, and the one here is your emitter. Notice how I have turned the transistor, right? Good. So we inject it onto the board this way. I have a 22 kilo ohm resistor which shall inject to the base. Because it's an NPN transistor and it needs a positive voltage at the base, I'm connecting this 22 kilo ohm resistor to the positive terminal. This is my power pack. This is the positive terminal. Okay, so when I'm done, I'll inject the negative one. This is my LED. I did mention how to identify the positive terminal of the LED in our previous video. So here, I'll put it inside. Then this way. Good. The emitter goes to negative or ground. So I'm attaching this so the emitter can go to ground comfortably or negative. So now, if you have gotten our holes right, if I power it up, the transistor should turn on the LED. So there you have it. Before we even go further, let's do some small analysis. Let's look at the base current. The base current, this is how the transistor has been biased. Yeah, do this. The LED is here. Plus VCC. Okay. Now we have this to the ground. And we have some voltage connected by 22K going to the base. So we have 22 kilo ohms. Now I want us to establish the base current feeding into the base to see if it is enough to actually power the LED up. So the base current is established by my voltage source is 12 volts. Our battery pack is 12 volts. So the current going into the base right now is 12 volts. This side will drop 0.7. It's a that will drop 0.7. So minus 0.7 divided by our 22 kilo ohm resistor. What you arrive at is about 510 microamperes. 510 microamperes, which is not enough to illuminate this LED. So it is this 510 microamperes appearing at the base, which is multiplied by a certain beta, creating a high collector current at the collector, which eventually gets the LED illuminated. So if the transistor decided to adopt from its range a beta of, say, 100, what will be the collector current here? Which give us 51 milliamperes, which is what the LED is probably running on. Okay. We could in fact increase the beta of the transistor and then inject the base with a much smaller base current and yet yield a higher collector current. How do we do that? We chain two transistors in series. Just as when two resistors are connected in series, their resistors add up arithmetically. We could also do that to transistors, such that when you connect them in series, their betas, they will not add, they will rather multiply. So if I connect two transistors in series in a way and manner I'm about to demonstrate to you, and each one has a beta of say 50, and the other also has a beta of say 50, it means their combined beta will now be 2500. All right, let's give it a shot and see, which also constitutes our basis for building our amplifier. So I'm come to add this transistor to this one in series and see what becomes of the circuit. Let me take the load out. The load is off. In fact, I'm also removing the base. To connect two transistors in series in what is affectionately called a Darlington pair format, What you do is this. You have the first transistor. Its emitter will be injected into the base of the succeeding transistor. The collectors are combined and given to the load this way. I'm assuming it's a resistive load plus VCC. And then we get the base current going. And then the emitter of the second transistor is taken to ground this way. So notice the configuration carefully, which is what we are going to implement on the breadboard and see what happens. Okay, so now we have this. So have this one is there. Now the TIP41, its pin configuration is a bit different from that of the 2N5551. For the TIP41, when you hold the transistor this way, the first pin is the base. The collector is the middle one, and it's also attached to the heatsink here. And this is the emitter. So long as the TIP41C is concerned, the base and then the collector, they trade places. So you want to keep that in mind. Okay, let's just put it there. So this is the base. Attaching it to the emitter here. Good. And we do know the emitter of this one will now go to the negative terminal here. Okay. The collectors are combined. So I'll join the collectors. This is the collector of the first one. Okay. I'm attaching it to the collector of the second one here. Okay. Now let's attach our load. This is the positive terminal. The positive terminal goes here. Then go pick it on the collector of the transistor here. Okay. I think everything is fine. Now, instead of injecting the base with 22 kilo ohms, I'll introduce 680 to the base. 680 kilo ohms to the base and see what becomes of the circuit. So this is the circuit. The base of the first one, which is here. Here. Take it to the positive. And then let's power it up and see. Good. See, the LED is much brighter with even the reduced base current. I've bent this LED. Let me just take it out and put the current hog there. So I'm taking this one out. I think this one is fried. I'm putting this one in instead. Let's power it up. Okay. So this incandescent bulb is a power hog. So you notice that it is on. Right? Draws more current. With the one transistor, this bulb wouldn't have turned on. But with the beta, it turns on beautifully. The variant in the calculation is that because the transistors are now connected in series, the voltage drop will now be 0.7 here, then 0.7 here. So when you're doing your math, it is 12 minus 1.4 divided by the resistor that we are using, 680 kilo ohm. So that is operating the transistor as a current control device by deploying its beta feature. Now we are going to vary the circuit a bit to get our first amplifier. We are maintaining the 680K there. But instead of the light, we'll put our speaker there. So the speaker is here by my side. This is a speaker. The speaker is here. Give me some space. This is the speaker here. I think it can't fit onto my board. So, but at least you understand. So I'm going to put a speaker at the collector junction where I introduce the LED. And then the other side will go to the positive terminal. So the speaker is between the collector and the positive terminal. We have to inject our signal through a capacitor which isolates the DC component from the AC component. I will explain that much later in the next video. But for now, let's just take it that the capacitor is for isolation. Notice where I'm introducing the capacitor. So the collector here join. The capacitor is between here. This is the capacitor. It's an electrolytic capacitor. And then in between the capacitor and the base, I'll inject my signal. So this is what's going to happen. This one also goes to ground. So the capacitor comes, then between the one lead is attached to the base and the other lead is between the signal and then the negative terminal, which is what we are going to do now. We have already replaced our load with the speaker. Okay, so this is how I introduce my capacitor to the base of the first transistor. I'll put it here. All right. I think I missed it. It should be here instead. Okay, here. Good. Now this is my signal source. I'm putting it here. And it goes to the negative. Let's power it up. Let me see what's happening here. It's playing. A moment. I think I missed the collector. I should have come here instead. So, okay, here. Okay. Okay, so now let's power it up and see whatever. There you have it. Your first crude amplifier. With only one resistor, one capacitor, 2 transistors, and you have some sound popping out of your speaker like nobody's business. With a 12-volt power supply. This transistor is becoming hot. It needs to be heat sinked. Let me shut it down. Okay. Let me put this. Pause this thing. So at least you get a concept, right? Good. Now let's see if we can operate the transistor as a switch. I have in my hand a relay. These are the terminals of the relay. A relay is an electronic switch, so that if I attach the terminals to a power source this way, you hear some clicky sound. Yes, it means the relay has turned on. Now, when the relay powers, there's a switch inside which attaches this pin to this pin and closes the circuit. When the relay is off, this pin and this pin behave as an open circuit. But when it is turned on, this pin and this pin are closed. It is also repeated on the other side. It has a normally closed contact, a normally open contact. These contacts are normally opened. This one and this one normally closed. I'm using the normally open contact so that when I energize the relay here to close this switch for me, which is what we are going to use in our circuit. Okay. So what it means is that we'll be attaching this bulb to our circuit. What we are going to do is we are going to connect one part of the incandescent bulb to a negative terminal, and the side which shall be connected to a positive terminal shall be fed through the relay. So the only job of the transistor is to energize the relay and then close the circuit there. I don't know if you get the concept I'm trying to paint here. Let's see what the transistor can do to the relay. So where the speaker is, I'm removing it. I'm removing the speaker. And in this place, I'll introduce the relay. So I don't need the capacitor anymore. This signal too, I'm taking it out. I don't need it. So let's see. How this goes to the collector, to the positive terminal. Good. Now let's apply power and see if the relay will click. It doesn't. So let's see if we can increase the base current a bit. So I have removed the resistor. I'm putting the 22K there at the base of the first one. So pay attention and listen to the sound, the clicky sound. There you have it. So the relay was just energized. Okay. Because of the huge beta, notice how even when I touch the probes, I touch the resistor and I attach my hand to the positive terminal, the relay clicks. I'm just touching, you see? So the transistor is ignited through my hand, and that turns on the relay. Okay. So in order that we don't lose our light when connected to the 12-volt power supply, I'm adding a 10 ohm resistor. This incandescent bulb can take a very large amount of current, but not on 12 volts. So let's attach some resistor so the rest of the voltage will bleed through the resistor. So here the circuit, let's try it and see if it will turn on. Okay, this is through the 10 ohm resistor. It gets hot almost instantly, so we'll not try it for long. Now let's see if we can connect it to the relay. So one of the terminals will go here. One of the terminals will go into the negative terminal. We want to attach this one to the positive terminal, but we want the relay to do the attachment or do that switching for us. So here. So when the relay switches, because this side here has me attached to a positive terminal, to just connect both here. I hope you get the concept here. So this way. When I finish, I'll draw it for you if it confuses you. So here. Now let's see if we can ignite the just by touching it. The beta multiplies the base current. You see, it is acting as a switch because over here it is either on or off. We are not faced with that situation where the current of the collector was dependent on how hard or how conductive our pumps were. This time it is either on or off. That is relay chattering at the moment. Oh, let's see. Okay. The 10 ohm resistor, if I keep the lights on for a longer time, it will just burn. But I get the concept. So if you can keep, if I just introduce the resistor into the hose here, it will just turn on. We have many applications of the relay. We shall consider some in subsequent videos, but at least you understand the concept of switching here. Okay, let's see. Let's see if we can draw the circuit on our board to make it much clearer. So, we had a Darlington pair this way. Taken to ground. Then, the relay was connected this way. The relay is an electromagnetic switch. Operates on the concept of electromagnetism. So, this is the coil around which the relay is, the inner coil is wound. This is a metal strip around which the inner coil is wound. And we have our switches here. These are the probes we use. We were using the normally open contacts, so we relied on this and this for our light. And we are saying that one of the circuits of the light, the bulb, so it was an incandescent bulb, so it will look like this. One was connected to the ground contact, and this one was fed to the relay contact, and the other relay contact, let me put it so to be simpler for you. This one was fed to the relay contact, and the other relay contact, this one was attached to the positive terminal. So this is how it looked like. So that when the circuit is ignited, these contacts will be brought together and then the lamp will turn on. At our base, we tried turning it on with our hand through the resistor. So we could just touch these terminals and it will turn on. But we finally implemented it with a 22 kilo ohm, which can be increased because by connecting the transistors in a Darlington format, the beta is enhanced. So this is how the transistor was operated as a switch. All that we have done is just to introduce the transistor. In our subsequent videos, we will build or construct far superior circuits. Okay, let's attempt to revise our assignment in lesson 2. Okay. So in lesson 2, we're given a simple battery charger. If you recall the circuit, the source voltage to charge the battery was 15 volts. The battery to be charged was considered discharged at 13 volts and considered charged at 15 volts, and it had a series resistor of 0.2 ohms. Your question was, what is the initial charging current? If you recall, you will notice that the circuit was configured such that the batteries were series opposing. This way, the circuit went on, and this one also turned this way. Had a series resistor here. RS to attach this, and then this one was 15 volts, and this one, when it was considered this charge was 13. So when it's 13, because they are series opposing, the voltage available to determine the initial charging current is the 15 volts here minus the 13 volts here. So it is 15 minus 13 divided by 0.2 ohms. Let's see what the initial current will be. That will be 2 over 0.2, which gives us 10 ampere, the initial charging current. And the question was asked, the final charging current when it has charged to 15 volts. The final charging current when it has charged to 15 volts was 0, because if you do it, it will be 15 minus 15 over 0.2, which gives us 0. So when the battery is done, when the battery reaches 15 volts, no current flows. I'll see you again in the next video when we build much more secure circuits using our transistors. I'll see you around. Bye-bye.